Well, today we're going to go a little bit deeper into this idea that we started in our previous discussion and kind of review and build up to where we need to go here. We looked at using, the left and right endpoints of subintervals to approximate, and we went through the example with n equal 4, and we used our function x cubed plus 1 going from 0 to 2, and we did several things that we will now formally define. We'll throw in some really high-tech terminology, if you will, but some terminology, some new notation, but it's really stuff we looked at last time, and we'll just kind of formalize it a little bit more today and then take it that next step farther. But we're leading up to the definition of the definite integral, and the first thing we would need to do in setting this up, like we did previously, is to partition this. And the partition with 4 rectangles, and we say use equal width. We'll talk about that as we get into the more general setup of this, but with equal width angles, our partition we found started at 0, then our next x value is 1/2, then 1, then 1.5, and then finally ending at 2. Now, we're going to generalize this later on into n partitions and how we'll represent that and what that ends up giving us. But what we found with the left endpoints, right endpoints, looking at this partition, we had f, well, I guess we started with the left endpoints really, f of 0, f of 0.5, f of 1, and f of 1.5, and then times the width, that equal width of 1/2. Now, somebody found a mistake we made yesterday. We had calculated this and come up with 6 point something. Well, it should have been 4.25. So correct that from the previous video. This should be 4.25. And then the right endpoints should be 8.25. Okay, so a little correction there from our previous discussion. And what we find is that the exact area will be between these two values. Okay. And we talked about how do we get closer. One way to get closer would be, as we said, use more rectangles. So the next part of this problem would be use 8 rectangles. Our partition would be, well, instead of these 5 numbers, we would have 9 numbers. Okay, we'd start with 0, end at 2, but our width with 8 rectangles would be, what, 1/4 rather than 1/2. Okay, and the setup would be very similar. We'd just have a little more work to do, a lot more calculations to do with the 8. Now, as we go more general, more theoretical, okay, we don't need to use just the left endpoints or we don't need to use just the right endpoints for this partition, or for the not partition, but what we call the sampling points. Okay. We used the left and right endpoints because it made the rectangles a lot easier to look at and calculations a lot easier. But theoretically, we can actually use any number in this first partition. And this first partition would be anything between 0 and 0.5. We kind of use the extremes here with the left and the right, but we could use 0.1 for the x value, or 0.3875 for the x value for this approximation. Okay, so we're not limited to just the left endpoints or just the right endpoints. In fact, we could go left endpoint on one of the subintervals. Then on the second part, we could jump to the right endpoint. Third part, we could actually do something in between. So the intervals, each one of the function values that we calculate, we're taking a function value of an x in that interval, in the first interval, in the second interval, or subinterval, I guess we should say. And we just, for nice calculation's sake, we just choose one endpoint and use it throughout. Okay. Now, one of the students after class was asking, well, can we use something else to make it even closer? We said, well, to make it closer, we could use more rectangles, but we could also, even with 4 rectangles, make the approximation closer than what we got here, and that would be using the midpoints for our sampling points, or for each interval, each subinterval. So this is what the midpoints would look like. Again, with just the n equal 4, 0 to 1/2 would be our first subinterval. The midpoint of that would be 1/4. So f of 1/4 times the width of that rectangle. Then our second one, third one, and fourth one, using the midpoints as our sampling points, calculating our function values or the height of those rectangles that we're using. And by the way, this would calculate to 5.875, if I did that right. Hopefully I did. But 5.875 for using the midpoints. Now, the main problem with the midpoints is we don't know whether this is an overestimate or an underestimate. It's going to be closer to the exact value, but we can't say for certain it's going to be more or less, like we were able to do with these endpoints. But I did go ahead and calculate the exact value of this area, and the exact value is actually equal to 6. Okay, so all of these, as we said, this is much closer than the left endpoints or right endpoints. But again, we don't know whether that's an overestimate or an underestimate unless we know the exact value, and then we can tell. But yeah, question. So as we get more into the details of this, we will be setting up sums like this as we calculate the exact value. Today we're going to see how to calculate this exact value by the definition of the definite integral, and then thankfully we have some shortcuts that we don't have to go through this long definition. Just like the derivative, we started out with the definition of the derivative, and then we found much easier shortcuts. Well, we'll see the same here. That's why I was able to find that value so quickly. But anyway, all of these sums, every one of these, has a special term. These are called Riemann sums. And we'll look at what a Riemann sum is defined as in general. The Riemann sum for some function, f of x, and for the partition, again we use this fancy, looks like a triangle, but that's the Greek letter delta. But the partition delta is the summation from 1 to n of f of c sub I times delta x sub I. And c sub I, as I talked earlier, that's what we call our sampling point. That could be the left endpoint, that could be the right endpoint, that could be the midpoint, or anywhere else in that first subinterval, second subinterval, or in general the ith subinterval. Okay, so that would be our f of 0, f of 1, what we calculated, and then our delta x sub I, that, well, we made all of the widths equal. So we just said that's going to be delta x. And delta x is the width of each of the subintervals. But theoretically, the width does not have to be the same for all of the subintervals. So we say delta x sub I, which delta x sub 1, the width of the first subinterval would be the difference between your x values, x sub 1 minus x sub 0. Whereas in our previous example, x sub 0 was 0, x sub 1 was 0.5, so delta x sub 1 would be 0.5. It happens that delta x sub 2 also was 0.5, and so on. The way we set it up to make things nicer, we set them up where all the delta x's were equal. Again, theoretically, we don't have to do that, but as we work through this, we're going to want to do that just to make it a little bit easier, or maybe less difficult, because I don't think any of this in the definition should be called easy. So, but it's doable. Don't panic yet. But now we did kind of talk about this. The delta is the partition, and in this case we're listing them out in very general terms instead of 0, 0.5, 1, 1.5, and 2 like we did on the previous example. And in the Thinkwell material, they call this delta x sub I is the length, but we've been referring to it as the width, so I'll kind of go back and forth on that. But again, these don't have to be the same length, but it's nicer when they are the same length. Now, theoretically, if they're not the same length, okay, to be able to get the exact value, we have to introduce yet another term. Now, if they are the same length as we were thinking, go back to the idea of finding that area, better approximation, we simply use more rectangles, and as we think about how we get the exact value, how many rectangles do you think we should use if we're going to get the exact value? Okay, right, an infinite number of rectangles. Well, we can't practically do that, but that's the idea. N is approaching infinity, then our approximation approaches the exact value. And we'll say A is our exact value. Well, that would be true if we're dealing with equal widths. Because as n approaches infinity, what's happening to all of those widths? Okay, they're getting smaller and smaller and smaller, and delta x, we would say, is approaching 0. Again, still theoretically correct, but we can expand this more by using this definition where delta x sub I, these don't have to be equal, but we have to adjust what we say here. Okay, we can't just say all the widths are approaching 0 because all the widths are the same. Okay. If they're not the same, we have to say, we'll throw out some really fancy words here, the mesh, or sometimes it's called the norm. This is defined as the largest width, the largest delta x sub I. Okay. And what we then have to think about, instead of just delta x approaching 0, we can say as the mesh approaches 0. And that will guarantee all the others will approach 0 as well, because the mesh is defined as the largest one of those. So we can get around having equal widths by saying, well, let's let the mesh or the norm be the largest and make it approach 0. And ultimately that makes all of them approach 0. Now the notation for the mesh, it's kind of like an absolute value. It's actually a double absolute value around delta, and that's our mesh notation. And essentially, again, we're going to be saying as the mesh approaches 0, we will be approaching the exact value using the Riemann sum, using the approximations that we looked at before. Okay, so here's the biggie, the definition of the definite integral. With all of these new terms and notation, definition of the definite integral of f from a to b is the limit of the Riemann sum as the lengths, or what we've been calling the widths, of the subintervals approach 0. Okay. And notation-wise, this is the notation for the definite integral from a to b. Now that looks an awful lot like the indefinite integral or antiderivative notation we've been looking at previously. There's a good reason for that, and that's not going to happen today or tomorrow, but as you watch the material for Monday, we'll see why we use that same notation. Okay. This is not the antiderivative of f of x, but it's the definite integral of f of x from a to b. Okay. Different, yet related, and we'll get to that later on. But the definition of this is, well, this limit right here. Now, the summation is pretty much what we've been doing, estimating the area under a curve. N equal 4, n equal 8. Well, in general, we're just going to say I will go from 1 up to some value n. And ultimately, we're going to let n approach infinity. Now, unfortunately, though, In the definition, we don't have n approaching infinity as our limit. We have this nice little notation, the mesh approaching 0. Well, if the mesh is approaching 0, the largest of all those widths approaching 0, what does that do to the number of rectangles? Okay, it makes n approach infinity. So we can kind of change the notation to fit our needs. We can say as the mesh approaches 0, then n is going to approach infinity. And we can change the limit then to the limit as n approaches infinity rather than worrying about that mesh. Okay? To begin with, before we get into the works of how we use the definition, we need to look at some summation formulas, and one of those summation formulas deal with a constant, and just thought I'd throw up a fairly easy, well, hopefully that's easy, example. Well, it is easy compared to some of the others we look at, but this says the summation of 3 as I goes from 1 to 5. Well, as we write out term by term, how many 3's do we have? 5, and that truly is the definition of multiplication, repeated addition. So the first formula that we're going to be needing deals with the summation of a constant. And that's summation of some constant c as I goes from 1 to n will simply be the product of c times n, just like the 3 and the 5. Okay. Now that one's a lot more straightforward to figure out where it comes from. We're going to be using a couple others that are, well, they're a lot more complicated to worry about. The summation of I as I goes from 1 to n. Now think about this. Summation of I as I goes from 1 to 4, let's say, that would be 1 plus 2 plus 3 plus 4. Okay, so that's what we're talking about. But this can be reduced to a nice little formula. Whatever n is, it's going to equal n times n plus 1 all over 2. And we'll be using that as we integrate, as we find the definite integral value using the definition. And sometimes we need to have the formula for I squared. Now this one is quite a bit more involved. N times n plus 1, but then times a third factor of 2n plus 1, and then all over 6 instead of all over 2. So write these down. For the test, I'm not going to have you memorize all of these, but we will be doing probably one of these definition problems, and I'll let you know as that test gets closer which one or which two you may need to know exactly. But these formulas we're going to be using, and our next let's go ahead and use the definition of the definite integral to calculate this value. The definite integral from -1 to 2 of 4 minus x squared. Okay. Now, that we can actually think of as find the area under the function 4 minus x squared over the interval from -1 to 2. In fact, we need to understand the definite integral is a mathematical operation, just like addition is a mathematical operation. That mathematical operation of the definite integral can be used in a lot of different ways, and we're introducing it as finding area under a curve. In our last chapter, we'll see some other ways to use the definite integral. But this is probably the easiest way to kind of lead into this mathematical operation. And to get an idea of what we're going to be doing here, the graph of the function 4 minus x squared is actually going to be a parabola. 0, 4 will be the top point, and then it looks like that. Now, -1, since we're starting our interval at -1, -1 has a function value of what? 3. And graphically, we're going to be finding the area from this over to where x equals 2. What's f of 2? Okay, 0. So we end up right here on that. So calculating this definite integral is the same as finding the area of this region. Okay. Now, just as we did with the approximations, approximating the area under this curve, we need to represent our partition. That's probably the best first step, although that's not the necessarily has to be the first step. But we will again assume or make all the widths equal widths. Theoretically, we don't have to, but in practical terms, it's going to be a lot easier if we do that. So we want to try to do as easy as we can. So delta x, well, in this case, delta x is going to be what? Well, the general formula for finding delta x is b minus a, which b is your right endpoint, a is your left endpoint. So basically the length of your x interval over n, which represents the number of rectangles we're using. But in this case, we're going to generalize the number of rectangles and say we're going to take that off to infinity. So let's just leave it in terms of n for now, and delta x is going to be 3 over n. I can't draw an equal sign. There we go. Well, as we start with our partition, we know x sub 0 is going to be the -1. But now, this is where it gets a little more complicated. Conceptually, it's kind of difficult to figure out. What is our next x value? In our partition, as we split up this x interval from -1 to 2,
we're going to have 4, right?
Actually, we're going to have an infinite number. So we're not dividing by 4 this time. We're dividing by n. Okay. So this is the step beyond what we were looking at yesterday. X sub 1 is going to be x sub 0 plus, well, what's the width in between x sub 0 and x sub 1? That's our delta x. Okay. So really, in general, any of these partitions, x sub 1 can be represented this way. And now, in particular to this problem, x sub 1 is going to be negative 1 plus what?
3 over.
Negative 1 plus 3 over n. Okay. Then as we move over, now definitely in general terms this is not to scale here. Looks like we're almost to 0 already, but it's going to be really, really, really tiny. But in general, x sub 2 will be what? Okay, we could say x sub 1 plus delta x. Or what's going to be even more helpful is saying x sub 0. If all of these start at x sub 0 and then plus, well, how far are we from x sub 0? We've moved over 2 widths, 2 times the delta x. This would be 1, and then this would be 2. And we look here, in particular to our problem, x sub 2 is going to be represented by negative 1 plus 2 times the 3 over n. Okay? Questions so far? Well, we continue with this partition, and the next one would be x sub 3. Can you see what x sub 3 would be represented as? Okay. Again, we'll be starting at negative 1 and moving 3 widths over to get to x sub 3. And ultimately, we don't really need each individual x value. What we need is, as we look at the generalization here, what is x sub I? We're going to look for a formula to say, well, whether we're in the 10th interval or the 100 millionth interval, x sub 10 or x sub 100 million would be what? And we can create this formula here. All of these start at negative 1 and then plus what? I times the delta x. So what you'll be really seeing in all of these problems, x sub I will be x sub 0 plus I times delta x. That's the general way to find the x sub I. But for our problem in particular, x sub I, our partition, can be represented in this form. Okay? Now we've kind of laid some groundwork here, but we need to remember where we're heading. The definition of this definite integral is given by this limit. And what we have found, well, we know delta x sub I, we're saying we're letting all the widths be equal, so delta x sub I is going to be 3 over n. Okay. No matter which interval we're at 3 over n for that. And then, well, we need to calculate the function value over each subinterval, and c sub I says we can use any number we want to in the ith subinterval. So our first subinterval will go from negative 1 to negative 1 plus 3 over n. So c sub I, we can use any of those numbers between -1 and -1 plus 3 over n? Well, one of the easiest things that we can do, what I would suggest you do every time, let c sub I be x sub I, which in general is using the right endpoints. Notation-wise, that's going to be so much easier to do. Theoretically, we could use any from, going back here, from x sub 0 to x sub 1. X sub 0 would be the left endpoint, x sub 1 would be the right endpoint. So the right endpoint of the first subinterval, represented by x sub 1, right endpoint of the second subinterval would be represented by x sub 2. So again, in general, the right endpoint of the ith subinterval will be x sub I. Okay. So we've got some calculations to do, some algebra here at this point. So with our function 4 minus x squared, using the right endpoints to calculate this, well, in general, what did we say x sub I was? That was what we came up with, the -1 plus I times the 3 over n. Now, unfortunately, we're not quite ready to go to the summation. We need to calculate what that is in the function. X sub I is just the input into the function, and then the output is what we're going to be using for the summation. So f of x sub I will be, now notation-wise, I'm going to change this a little bit. We'll combine I times 3 over n as 3i over n. 4 minus x squared, to evaluate the x sub I, we'll have that. And like I said, lots of algebra from here. And don't forget, we're subtracting the result of this. So minus and then this quantity. Squaring the binomial. Okay. Different ways you can think about that, but remember, it's not just the square of each term. If you need to write it out this way and FOIL, go right ahead. But the first term is going to be +1. Then we'd have the outsides and the insides. We'll end up with -2 of the 3i over n. And then finally, our last, we'll have, what, 9i squared over n squared. And so our function value for the right endpoints, we'll do multiply the negative through. Let's go ahead and multiply the 2 times 3, make that 6i over n, and then minus 9i squared over n squared. Okay. And then finally, we can go back and say f of c sub I, might as well do that little operation. 3 plus 6i over n minus 9i squared over n squared. So let's pull all this back together into the summation, into the Riemann sum. So by our definition, we have this, and now in particular, f of c sub I was what? So there's f of c sub I, what we came up with for our problem. And then delta x sub I. Delta x sub I was our 3 over n. And that is what we have left to calculate. And we're out of time today. We'll finish this up tomorrow at the beginning of class and see how we can work through. A lot of it from here is algebra, but we'll be using those summation formulas and then calculating a limit. So we're almost there, but we didn't quite get it today. Probably 5 more minutes. That'd probably do it. So.